Hello and welcome to a special edition of The Naked Scientists, which comes to you from the Cambridge Science Centre. We are, of course, in the august city of Cambridge, which is originally home to Isaac Newton, inventor of gravity. Also the place where this amazing thing, deoxyribose nucleic acid, was discovered and read. Of course, deoxyribose nucleic acid is better known as DNA, which shares its name with the acronym for the National Dyslexic Association. Still off the mark with that one, weren't they? It's also home to Cambridge University, which means that pretty soon a new term is going to start, and we'll see a whole bunch of students who are going to start suffering from the terrible condition known as the Heineken uncertainty principle. This is rather like the Heisenberg uncertainty principle, with the exception that you wake up not knowing where you are or how much you've actually drunk. What we're going to do for the first time here from the Cambridge Science Centre is to give you the opportunity to meet a panel of august and esteemed scientists from Cambridge University and ask them questions. And you can ask them about their research, you can ask them about their science in general, and we also have some kitchen scientists because we're going to do some experiments as well. Please join me in welcoming. I'm going to go through our panel who are going to speak to you this evening. Our guests are Professor Rod Jones, he's an atmospheric chemist. Which means he's great at parties. Rod, what do you do and what do you work on? Just summarise your work for everybody.
Well, I'm a professor of atmospheric science, and I try and make tiny sensors so that we can look at air pollution and try and link it to human health.
Next to Rod is from the Department of Materials Science, Caroline Goddard. What do you do, Caroline?
Hi, I'm involved in developing alloys for the jet engine.
Wow, you can't get better than that, can you? I make jet engines for my PhD. And Professor Margaret Stanley.
I'm a virologist, pathologist. I work on viruses that cause cancer, and I try to develop vaccines to prevent infection with these viruses and prevent the cancers.
And specifically, these are human papillomaviruses that cause cervical cancer, yes, oral cancer. So Margaret's work has actually helped to develop that vaccine, which is going to go around the world and potentially save thousands of lives. So get your thinking caps on, anything you'd like to know about the atmosphere and how we measure things in it, how we build a jet engine and how a jet engine works, and how the metals that go inside jet engines work and how we can make them better, and viruses and how viruses cause disease and maybe even cancer, and how vaccines can stop diseases and potentially also stop cancer. Over here, Dave and Ginny are our kitchen scientists, Dave Ansell and Ginny Smith. Take it away, guys. What have you got for us?
So I've got a lovely little demo here. I have a mug on a piece of string. And on the other end of the piece of string
got a few mugs in this room as well.
A little nut of the metallic variety. So in fact, it's an M8 nut. In fact, I know that from just looking at it, it's slightly worrying. I'm just going to run the string over the top of a mug and undo the knot in it, because otherwise it's going to go horribly wrong.
So basically, Dave, you've tied a mug, a china mug, onto a lump of string, and you've got a little nut on the end of that 1 metre long bit of string and a biro. And you've put the string over the biro.
The string's going over the biro. So at the moment, I'm holding on to the nut. So that's holding up the mug. And then I'm going to let go of the nut.
It might go smash.
Okay. So 3, 2, 1.
Whee! Now, for the benefit of people that aren't actually able to see this, because they're on the radio, Ginny, tell all.
So the mug looked like it was going to fall. Obviously, once Dave let go of the string, gravity was pulling it down, and it fell quite a long way, but stopped about a foot from the floor. And if we look closely, we can see what happened is that the nut has swung and wrapped itself around the biro several times, and that's holding it in place. Why has that happened?
So as the nut starts to fall, it starts to spin around the biro. And as the string gets shorter and shorter and shorter, it's a bit like climbing the middle of a roundabout. As you climb the roundabout goes faster and faster and faster. So the string spins round and round, faster and faster and faster, until it's going fast enough to wrap around enough times that it doesn't fall out on the floor and smash.
Probably not one to try with your mum's best china.
No,
but
go on, give it a go. Thanks, guys. They're coming back throughout this evening, so if you have any questions for Dave or Ginny on how to do experiments at home or how physics, chemistry, biology work at large, they will be very happy to take those questions, so get your thinking caps on now. Great demo, guys. Now, up first, Professor Rod Jones is a professor of atmospheric physics in the chemistry department at Cambridge University. Being a chemist, I was thinking, what chemistry jokes do I know, Rod? And actually, I was in Australia last month, and I asked the audience there, do you know any good chemistry jokes? And this works best with an Aussie accent. But this girl said, what did two doctors discussing a very ill chemist say?
Are you asking me?
Well, if you can't heal him or cure him, then you'll have to bury him. Tell us about your work. What do you actually do?
Well, I do lots of different things, all the way from looking at the ozone layer through to looking at climate change. But tonight, what I've brought along is of the very small sensors that we make so that we can actually look at air pollution and try and then understand how air pollution itself works. And then we try and build slightly more sophisticated gizmos which allow us to monitor what a person walking the streets might be exposed to. So inside this box, which the people can see here, those on radio, it's about 20 centimeters by 8 centimeters by 2 centimeters. It's got one nice green button, which is the go button. And inside it, there is a mobile phone. I'm going to hand it out in a minute. And what this does, it's also got a navigation system inside so that we can know where it is. We have 3 different gases being measured. Somebody can put this in their pocket. We know where they are. We know what they're exposed to.
How do you know where they are?
Well, because we've got what's called a GPS aerial inside it, which is what you need in your car sat-nav to help you navigate. And so inside here, there's a mobile phone, we have a sat-nav effectively, and we have some chemical sensors. And so we can actually monitor every second or so what a person's being exposed to, and then we can relate that back to what we know is causing pollution in a town, and we can also relate it back to somebody getting more asthmatic or wheezy as they go through a more polluted area. So we're trying to conduct experiments which are linking those two.
Why is this better than what we have already?
It's better because you'd have a real problem in putting conventional instruments into your pocket because they weigh about 60 kilograms and they're about the size of this table.
So how have you managed to make it so small?
Well, we've taken sensors which traditionally are used in alarm systems and we've just made them better and about 1,000 times more sensitive. And we can now make them about 1,000 times smaller, which is what you can see here, what the audience can see here. And because we can make them really small, we can now make them much more portable and we can just give them to people to carry around.
And what can you detect with it?
Well, these little chappies can just detect gases like carbon monoxide and nitrogen oxides. We've got other ones which can do other gases as well, but nitrogen oxides particularly are well known or thought to be associated with health impacts. So that's one gas that we can go for.
Let's take some questions. Get your hands up in the air if you'd like to ask anything. Let's start down here at the front. Who are you, sir?
I'm Ujjwal. I live in Cambridge. I just wanted to ask some very naive questions. What is air pollution and how do you measure it?
Well, air pollution that we're worried about is probably nitrogen oxides which come from cars. It's probably particles that come from cars and buses particularly. A lot of it is linked to transport. But those are the principal gases that you'd expect us to link to air pollution, and those are the ones which are monitored by the national networks.
Who's next? What's your name, sir?
Elliot. How long does it take to make one?
Oh, gosh. Well, to design and build one from first principles, it takes a few years. But once you know how to do it, it probably takes a few minutes.
So there's hope for you yet, Elliot. You can do it with Lego, perhaps. Yes, madam.
Hi, my name is Ailish. I live here in Cambridge. I was just wondering, you mentioned putting the device in your pocket. How accurate a test would that be compared to breathing in harmful chemicals?
That's a very good question. And of course, if you put it in your inside pocket, not very accurate. So what we're actually doing, and I've not brought them along this evening, is make much smaller versions of these, which effectively you can put on your lapel, much closer to where you breathe in. So we're trying to get closer, and as we build these things smaller and smaller, we can put them in much more sensible places.
Can I just ask a quick question, Rod? What happens if you put it in your trouser pocket and you've had beans?
Well, we don't measure methane.
But isn't that quite an important greenhouse gas?
It is an important greenhouse gas, and in fact, I don't know whether you're trying to lead me into another area, but we've got other sensors just like this, which are designed to measure greenhouse gases so that we can, for example, work out how much CO2 Cambridge is emitting. Not methane yet, but we could go that far, but I'll keep that for another story, I think.
What's your name?
Laura.
Hello, Laura.
Once we've created pollution, can we get rid of it?
Gosh, that's another very good question. Well, it gradually decays in the atmosphere. Even when it rains, you get rid of a lot of pollution. But some pollution takes quite a few months to get rid of. So there is a natural process of getting rid of it. But if you're emitting it locally, then you can easily get very high concentrations, even though you're losing it gradually. It's a bit like filling a bath.
What's the amount of time that carbon dioxide, once it comes out of the exhaust pipe of a car or whatever, for instance, stays in the atmosphere once we've released it? How long is it around for, causing a greenhouse effect?
Well, of course, carbon dioxide isn't a pollutant, air quality pollutant in the way that we were talking about a couple of minutes ago. But once it comes out of your tailpipe, it's probably in the atmosphere for 100 or 200 years.
So anything we emit now, we've potentially got to deal with for 100 or 200 years. We've got to live with their consequences for that long.
Yeah, I think that's absolutely right.
Yes, sir.
Good evening. My name is Carlo, and I would like to know, when we walk the street, are children more exposed to pollution than adults are, because maybe adults are taller, or it does make no difference?
We're looking at that, and the effect doesn't seem that great. I mean, of course, if you park your buggy at the exhaust of a bus, you're in trouble. But actually, what's really important quite often is which side of the street you walk on. And so one of the things we're leading towards doing is developing a phone app to tell you which side of the street you want to walk on if you're going to take a low pollution route. So it's a good question.
That could mean that everyone takes that route and then they walk really slowly because they're all stuck behind the slowest person in the world who is inevitably going to be on that same pavement. Then you get more exposure because you've got to breathe the air for longer.
Well, that's probably true, but so maybe we should...
You have to factor that into the app. One more question here.
Hi, Errol. How many data points do you actually need to get a good map of a town? So how many people carrying it for how long to give you a really good sort of map of pollution across, say, a city centre?
We've been trying for years to get that number, and we haven't got there yet. Every time we can make a measurement with more sensors, we see more detail. So we're trying to unpick that problem at the moment.
Thank you very much, Rod. Rod Jones from Cambridge University. Right, time to get a bit experimental. And if you want to use one of these guys, Ginny and Dave, to make them victims, feel free.
I think we might have something for them to do a bit later. But first of all, there seems to be a lot of rubbish on this table. Have you just been eating crisps and left stuff lying around? And what's with these plates? I don't think I'd want to eat my dinner off that.
Well, also on this table, I have a microwave.
Yeah, I thought that was just for your dinner as well.
I get quite peckish, so this is understandable. So the rubbish we have is a crisp packet, and crisp packets are quite beautiful things. They're shiny on the inside and they're kind of plasticky on the outside. And we have here is a microwave oven. Now, the way a microwave oven cooks is by essentially causing electric currents to flow backwards and forwards inside the food. And food isn't a very good conductor, so it doesn't get very hot. However, the shiny aluminium inside a crisp packet conducts electricity really quite well. Aluminium is almost as good a conductor as copper.
Now, I've always been told not to put anything with metal on it in the microwave.
This might explain why. This probably a crisp packet is the one thing that, with permission, isn't too bad in a microwave, but anything else with metal is a really, really bad idea. So I'm going to take the microwave, not the microwave, I'm going to open the microwave and I'm going to put the crisp packet into the back of the microwave. Hopefully that should be standing up.
Okay, so we've now got a crisp packet in a microwave, and we probably want to put the house lights down around now so that people can see what's going on. And then you're going to turn on the microwave?
So I'll turn on the microwave. This should cause lots and lots of electric currents to flow inside the crisp packet, and that might make it a bit warm.
So we got what looked like a whole load of sparks going out from inside the crisp packet. If there was just a current flowing through there, why did we get sparks?
So first thing, I'm going to very, very carefully go in, because it could be very hot, and take the crisp packet out.
Okay, that doesn't look like it would be much use for holding crisps anymore. It's all scrunched up, it's kind of melted into one blob. It doesn't look very appealing.
So it's shriveled up in the same way as you put a crisp packet on a fire. It gets hot and it shrinks and shrivels up. And as it's doing that, it kind of bends and you get big electric currents flowing through it. And all of a sudden you can get bits get close to each other. And there's kind of a shortcut the electricity can take through the air, and it jumps through the air and produces sparks. As it shrinks, the bubbles get close to each other, you get sparks, and you get these rather exciting noises, which I'm sure you heard.
So it's a little bit like lightning, except it's jumping a much smaller distance than lightning does.
Exactly right, yes.
Ginny and Dave, thank you very much. Anyone got any questions, any physics questions or anything like that that we can ask Dave and Ginny? Get your hands up. Anybody got anything you'd like to know? We have one down the front here. What's your name, madam?
Hi, I'm Jyoti. I live in Cambridge. You can put food in the microwave on an alfoil and it's absolutely fine. It heats up. So how does that happen?
I think aluminium will get hot in a microwave. If the microwave can get to it, it will get hot. But if there's nowhere, if it can't shrink, because with the crisp packet it was shrinking, and you get the small gaps where the electricity can jump as sparks, you don't necessarily get sparking. You do get sparking off things like gold rims on plates, because then you get a little break in the gold rim, and then you get sparking across that. I wouldn't necessarily say it was a good idea in general, but I could quite believe that it worked.
So you only really get sparks when you've got something that can conduct the electricity, but then a point where it can't conduct it anymore and it has to jump through the air. So because the crisp packets have a sort of plasticky coating, that can't conduct the electricity anymore. So then when the electricity reaches that point, it has to jump, and that's why you get the sparks.
We have a question down the front here. What's your name?
Nathan.
Hello, Nathan. What can we do for you?
I was just wondering if you'll be able to do that again.
Oh, can you do it again?
Dave's just going to set it up again. We're going to pop the crisp packet back in the microwave and turn the house lights down, and then we'll set it going. There we go.
Okay, next question. Who's got a question? Yes, sir, down the front here in the black T-shirt. What's your name?
Ashley.
Hello, Ashley. What
would
would you like to know?
if you tried to cook food in a crisp packet like that?
Well, as you saw, the crisp packet kind of shriveled up and melted. So I think what you would find is you'd have bits of melted crisp packet stuck to your food. And it will probably also burn in places.
And hot plastic doesn't taste good, I've found from experience, so I wouldn't recommend it.
No, I don't think it would be the best way to cook your dinner.
Okay, there's one more question here. This gentleman just in the second row here. What's your name?
Aaron.
Hello, Aaron.
So if it takes electricity 10,000 volts to jump a centimetre, how many volts were in that crisp packet when it was sparking?
There will have been thousands of volts. The electricity kind of sloshes backwards and forwards through the crisp packet. And as it does that, when it kind of sort of slams at one end, you get very, very high voltages.
Just over here. Yes, sir.
My name is Fergal. If I know hot plastic doesn't taste good, but is there any health risk associated with cooking food in plastic dishes in a microwave?
Ready meals.
Yeah. So I think the answer is that they do tests on things like that. So I think anything that, your food's sold in a plastic thing that says you can put it in the microwave, they would have tested that and they would have shown that the chemicals weren't going to harm you. If it's something that's not microwave safe, then if it melts and you actually end up ingesting more of that plastic because it's melted into your food, that's probably not going to do you much good.
Makes horse meat taste great.
There are some plastics which, when you get them hot, do give off bad chemicals, but they would have deliberately picked them not to use in food packaging. And the really nasty thing about the hot plastic, when it starts to burn, you get lots of nasty chemicals. And hopefully you're not burning your food too badly when you're cooking a ready meal.
Probably less bad for you than the food in the ready meal, to be honest. Dave and Ginny. You're listening to The Naked Scientists with me, Chris Smith, and with Ginny Smith, Dave Ansell, and our panel of experts this week, Rod Jones and Caroline Goddard and Margaret Stanley. We're at the Cambridge Science Centre, where we have an amazing panel of people who've come to see the show and ask their science questions. Hello to all of you. Thank you for joining us, everybody. Right, let's move on to our next guest this week. And joining me now, Margaret Stanley, who's a virologist. Actually, Margaret, I was scratching my head because I had a dodgy chemistry joke for Rod, and I found this one. I thought I'd try this out on you, right? So a virus goes into a bar, And the barman says, "Get out! We're not serving your type in here." And the virus says, "Well, you're a terrible host." Tell us about your work.
After that terrible joke.
Well, things can only improve.
Well, I work on viruses called papillomaviruses, and they're incredibly interesting because they only live in the epithelium that covers your body, like the skin and the interior of your mouth and the interior of the reproductive tract and your back passage. And most of the time, these viruses do no harm. In fact, if you ever see an effective one, it's likely to be a wart. But they're a huge family, and like all families, they have black sheep. And the black sheep of this big family cause cancer. And the cancers they cause, the big one is cancer of the cervix in women. Now, that is a huge problem in the world. It's the second commonest cancer in women worldwide. In sub-Saharan Africa, it's the commonest cancer in women. So we're talking about a really serious disease. Now, it's not just the cervix. In men and women, it causes cancer of the anus, which is the back passage. It causes cancer of the tonsil. And it also causes cancer in women in the vagina and vulva. So we're talking about something really important. In fact, 5% of all cancers are caused by these viruses, one in particular.
How does it cause cancer in those places,
Well,
Margaret?
that's a very interesting question. First of all, the virus doesn't intend to cause cancer. Cancer for a virus is a dead end because viruses exist to make more viruses, and that means they have to reproduce. Now, when viruses cause cancer, they are no longer able to reproduce in the cells, so it's bad news for the virus. It's because these viruses, particularly this 116, carries two genes which are really important for the virus to reproduce. But if those genes are expressed in the wrong place in the epithelium, because the epithelium I'm talking about looks like a brick wall, and normally these two genes in the virus are made in the upper parts of the bricks. But in the cancers, they're made right in the bottom. And that's absolutely the wrong place, because that's where the cells are dividing. And these genes distort the way cells divide. And
So the virus puts those genes into the cells and makes the cells grow more than they should.
Grow more than they should. And not only that, it stops them distributing their DNA and their chromosomes properly.
Yeah.
So they end up with abnormal numbers of chromosomes, and they end up able to accumulate more and more errors. And that's how cancers develop.
So how did you turn the virus into a vaccine that could prevent those diseases? How did you do
Well,
that?
what you have to do is prevent infection with the virus. You can't act on the cancer, but what you can do is prevent women and men being infected by this virus by giving them a strong immune response. And so what you do, this is what's been so interesting, is we make shells of the virus particle. The virus looks like an egg. It's got a shell. And what you do when you make the vaccine is you make the shell, but you don't have the interior, you don't have the DNA. And this shell to the body's immune system is exactly like the real virus. And it makes antibodies to the proteins in the virus shell. And the big technical advance was being able to make these shells. We call them virus-like particles. And they're incredibly effective. They generate really strong defense responses. And we know that these vaccines work. We know they work because the vaccines are now being laid out in certainly the industrialized world. And in Australia in particular, where they've been vaccinating since 2007, we can already see the decline in infection with the virus, and we can see the decline in the pre-cancers caused by these viruses. So it's a triumph.
Let's take some questions. First one over here.
My name's Julian.
Hello, Julian.
You were talking about vaccination, and we have a policy in this country to offer vaccination to teenage girls for human papillomavirus. Do you think we should extend that to teenage boys as well?
Yes. You're talking to the converted. The policy of giving it to girls was developed because at the time when all these policies were being generated, focusing on cervical cancer was the focus. But now, in the time that's elapsed, we've got a lot more information, so we know how much male cancer there is. And basically, if you leave 50% of your population unprotected, then you've always got a great big pool of susceptibles. So it's a much more sensible policy to immunize everybody. Then you don't have to worry how long the protection's going to last because everybody's protected.
Yes, madam.
My name is Jyoti and I'm from Cambridgeshire. Is there any selective population who is more susceptible to the viruses?
No, that's another thing. If you went out and took 1 million women, we know that probably 800,000 of them would get infected just because that's the way that virus transmits. But we don't know why some people are susceptible and can't get rid of it. It's not to do with ethnicity. It's not to do with behavior. It's, sorry? Haplotype, no. We do not have a handle on what the immunogenetics are. What is it about an individual and their ability to defend themselves against this virus?
Why is it, Margaret, that you catch it, but then you don't get the cancer for years?
Because you get rid of it. Most of it you get rid of. But also, you're looking at, in those people who develop the cancers, you're looking at chance events. You know, you're looking at the probability of a molecular accident. Now, you can do the statistics. How often do mutations occur? So these are chance events, and that's why it takes time.
Yes, sir.
Hi, my name's Alex. I'm from Cambridge. I have 2 very quick questions for you. The first is, you said we're all exposed to these viruses, and yet we need a vaccine to make an immune response. So why is that? And secondly, you also said that we couldn't make a vaccine against the cancer. Why can't we make a vaccine against the cancer, since the cancer would also have these viral particles in it?
Okay. First question, I've forgotten it.
Well, if we can make an immune response to the vaccine, why can't you just use your own immune response to boot the virus out?
This is a virus that only lives in the skin. Because of that, it is not very well exposed to the immune system. Now, you have to get into the circulation to the lymph nodes to generate a good immune response. And so actually in natural infections, you don't make a good immune response to this virus. Even though it's a pretty lousy immune response, still most people actually manage to get rid of it. The real issue for whether you're going to get cancer or not is whether you're one of those individuals who cannot clear this virus, cannot get their immune system to really deal with it. And I don't know who these people are, which is why you immunize everybody to give them a strong immune response. Because when you immunize, you put your vaccine into the muscle. So you go way beyond the skin, and that way you get straight into the lymph nodes to where the body really generates its defenses.
And just very briefly, Margaret, the second question, which is, we can vaccinate against the virus, why can't we just vaccinate against the cancer?
Because cancers, as they develop, have evasion strategies which evade the immune response, which deregulate the immune response. So it's a bit like turning a huge tanker around, trying to generate an immune response against a cancer that's going to be effective, because that cancer's spent 15, 20 years avoiding the immune response in the host.
It's become quite well practiced. We've got time probably just for one more question. Young lady just down here.
Hi, my name's Grace, and I just wondered why some people get cancer and others don't.
Oh, if I knew that question, I'd be on the plane to Stockholm for the Nobel Prize. Some people are susceptible to these virus infections. Cancer's not one disease. It's a word that describes many diseases which occur in particular sites. So I'm talking about cancer in the cervix, and I know what causes that cancer, which is a virus. But if I was talking about cancer in the breast, I don't know what causes cancer in the breast. I don't know why some women get it and others don't. Each cancer has its own profile, has its own risks, and these are different to a cancer in a different site. So I can't answer your question properly.
Sorry and all that, but it was very good that you answered the rest of them. Thank you, Margaret. Margaret Stanley. Okay, time to get experimental again. Dave, Ginny, take it away.
Okay, so next to the microwave, you've got another quite interesting contraption. What I can see is what looks like a sort of old-fashioned alarm type bell inside a Perspex tube. Why are we looking at this?
So basically, I have a sealed Perspex tube, and inside it there's a bell, and if I press the button to make the bell ring, you hear the bell really quite well. And you can also see the little fan in there blowing air around, and you can see there's some air moving inside. So what I'm going to do now is a really, really classic experiment. What I've got this tube attached to is something called a vacuum pump, which is a bit like a really, really hardcore vacuum cleaner. A normal vacuum cleaner can take out about 10% of the air from something. This will do about 99% if you give it long enough. So if we listen to the bell at the moment, it's quite noisy. And I will slowly pump the air out.
So that's quite noisy as well.
Yeah, vacuum pumps aren't the quietest of devices. What you can hear when I'm talking to you is that when I'm talking, I make the air in front of my mouth vibrate. And so the air's moving backwards and forwards, and the air in front, that bashes into the air in front of that, which bashes the air in front of that. And eventually, unless you're listening to me on a radio, when the loudspeaker in the radio makes the air vibrate, so the air bashes and bashes and bashes until it gets to your ear, and that makes your ear vibrate, and you can hear me talking. So what we're doing here is we're slowly taking the air out of the tube. So the bell should hardly be able to make the air move to start with, and then the air's so thin that it shouldn't be able to, any vibrations in that are going to have hardly any effect on the rest of the world, and hopefully it should be quite quiet.
What I can see is that where the little fan was blowing some bits of tin foil around, they don't look like they're moving anymore. So have you turned the fan off?
If you look carefully, the fan is still running. So what I've done instead of doing that is I've taken the air away. So now if we try ringing the bell, almost entirely quiet.
Yeah, you can sort of hear that something's going on, but it's definitely not the kind of bell noise you could hear before.
And you can see the clapper moving, but it's very, very quiet. If I let the air back in again, though, which takes a while.
So then if I press the bell while you're letting the air back in, we should be able to hear it starting to get louder. Can you all hear that?
So, Dave, answer the age-old question, could someone hear you scream in space?
That depends on if you're actually out in space, then there's no air there, so no. But if you're in a space station, then yes, because there's air.
Dave and Ginny, thank you very much. Who's got some questions? Hands up if you would like to ask them any more physics questions. We have one just here, this person. What's your name?
Laura.
Hello, Laura.
When you practice at home, does anything ever go seriously wrong?
Come on, Dave. Now it's time to be honest.
I've broken lots of things. I haven't killed myself yet, which is always a good thing, and I haven't badly injured myself. So I think that's pretty good going.
This question just over the back here.
Hi, my name's Paul and come from Hardwick. We're talking about vacuums, and they keep telling us that space is vacuum, but they keep talking about solar winds. How can be a wind in space in a vacuum?
You can never get a perfect vacuum. And there's always a few particles left. If you go into deep, deep space, there might be only one or two in every cubic meter, whereas in a normal air, there's hundreds and hundreds of billions, if not more than that. And so the vacuum in space is very, very good. Better than anything you could get without really, really, really expensive kit. You're talking millions of quid on Earth. But that doesn't mean there aren't still some particles there, and the sun does throw off little tiny hydrogen nuclei, and they get thrown out incredibly high speed. And so there is a little bit there.
I think the speed of it is about 1,000,000 miles per hour, isn't it? That it goes streaming past.
It's really scary fast, but there's not very much of it, so it doesn't do too much damage or move things around very much.
But it's also responsible for the aurora, isn't it? When it strikes the magnetosphere around the Earth.
Yeah, it gets deflected by the Earth's magnetic field and then piles into the north and south poles and gives lots of energy.
Makes Norway a lot of money out of its tourist trade. Very nice. There's another question over here.
This is Fergal again. I'm wondering, how does the speed of sound depend on the air pressure? So as you travel out into space and you were to do an experiment.
Interestingly, it hardly changes at all, because the speed of sound is to do with the ratio between the density and the kind of springiness. And as you reduce the pressure, you reduce the density, but you also reduce the springiness, and it cancels out. What it does depend on is temperature. And the lower the temperature, the slower the sound, because you kind of reduce the springiness without reducing the density. At high temperature, it goes very fast. At low temperature, it goes very slow, which is the reason why if you fly up in a jet, where jet planes fly, it's about minus 30 degrees centigrade, at which point the speed of sound is about 600 miles an hour, not 700.
Does that affect when you would get a sonic boom then? So higher up in the atmosphere, you go slower to break the sound barrier?
Yes, it is easier to break the sound barrier when you're higher up. You don't have to go nearly as fast.
Fantastic. Any other questions for Dave and Ginny? Or can we move on? One in the front. Oh, another one.
So it's me again, Paul. We just heard that Voyager's left the solar system. How? What's making it move all these years?
Okay, so essentially Voyager had a big rocket on it and it was going really, really fast. And it kind of did some cunning maneuvers going around different planets, especially Jupiter, which gave it an extra kick. And basically, it's just going so fast that it has enough energy to keep on going forever. It'll keep on going straight out the solar system and go. So, yeah, if you shoot something out of a gun fast enough, it won't come down.
Thanks, Dave. Thanks, Ginny, very much. You're listening to The Naked Scientists. This is a special edition of the show, live from the Cambridge Science Centre, where we've brought half the population of Cambridge, well, not quite, to come to see a show with me, Chris Smith, with Dave Ansell, with Ginny Smith, and our panel of guests, Margaret Stanley, Caroline Goddard, and Rod Jones. And, of course, you, the public. Our next guest is Caroline Goddard. Now, do I have a joke for Caroline? Well, I was thinking about this, thinking, well, materials and atoms and stuff. So I thought, something really small. And then I thought, well, okay, so an atom goes into a bar and says, I think I've lost an electron. And the barman goes, how'd you know that? And he goes, are you sure? And he says, yeah, I'm positive. Tell us about your work.
I work on developing alloys, which is when you mix a couple of metals together, a bit like baking. You mix things together, heat it up, see what happens. So the reason we do this is because essentially when it's in its pure state, metal isn't that good. You need to add something else to it that's got some good properties that you also like to it to make it much better. For example, steel is made up of iron and carbon, and the carbon is what makes it strong and more brittle.
So what is the difference between iron and steel? If I looked down a microscope, they're both iron, right? But it's just the trace element carbon that's there. Why does it make a difference?
So the carbon sits in the spaces between the iron atoms, which stops the atoms from moving around, which makes it much, much stronger.
Why is it then that a piece of iron, if I just put it out on the street, will go rusty, but stainless steel doesn't?
Stainless steel includes another element which is really, really environmentally resistant, which is chromium, because chromium reacts with the oxygen and creates this layer of oxide on the surface, which prevents it from rusting or corroding. So if you put some chromium into your steel, then you'll get this layer on the surface which prevents it from rusting.
Tell us about the jet engines, because I'm dying to know what you do with those. How does one work?
A jet engine...
Just a simple starter for 10 points.
So a jet engine works by air goes in through the front and is compressed as it moves through the engine. It's compressed really, really, really small. And then at that point it gets really hot and you inject some fuel into it and ignite it. And the air expands very quickly and goes out the back of the jet engine, which creates some thrust. And then this expulsion of air creates enough power to turn the turbines in the engine, which turns a huge fan at the front, which you've probably all seen when you fly off on your holidays, which sucks in a huge more amount of air, which flings it back, which makes the plane go forwards.
Brilliant. Suck, squeeze, bang, blow. Yeah. I think that's what Rolls-Royce say, isn't it? How an engine works.
Yeah.
So what are you doing to make these things better? They work pretty well. I've just taken a very long flight and I think there were Rolls-Royce engines on the plane, because you can tell because they paint those little spirals on the nose cones and they also go clockwise. Interesting fact I learned about Rolls-Royce Aero. You can tell a Rolls-Royce engine because they go clockwise. All the other engines go the other way. But why are these not good enough? What can we do to make them better?
To make an engine go fast, it has to be very efficient at burning fuel. And to make it more efficient, you need to make it go higher temperatures. So in order to do that, you need to develop a material that can reach higher temperatures.
So how hot is it inside the jet engine then?
It depends on where in the jet engine. At the front, it's relatively low, about 300 degrees, something like that. When you get to the combustor and the turbine at the back of the engine, you're reaching 800, even higher degrees. So it's very, very hot. So what happens is the engineers design an engine that can tolerate all of these temperatures, and they come to the material scientists and said, we need a material that can reach this temperature.
Oh, so they say, this is what we want to do, go and make the material that can do it. And no material like that exists yet.
Exactly. So
that's
then
good.
they get lots of PhD students like myself to go around and make lots of materials that will reach this temperature. And then the engineers will come back to us and say that they want it to go even higher. So we have to go back to the drawing board again.
So there's the challenge. How do we actually make materials better? Over to you. What would you like to know? Yes, sir. What's your name?
It's Errol again. It can't be trial and error. You must start with some base materials with some obviously standard sort of functionality. How do you decide which ones to put together to come up with the problem you're trying to solve?
So choosing your base metal gives most of the properties. So if you use iron, then most of your properties are very steel-like. You use titanium, you'll have a very lightweight material that's strong for its weight. So you choose your base metal based on that. High temperatures in the turbines, we use nickel as our base. And then you put chromium in to make it environmentally resistant, and then put some other elements in that will make it stronger or make it better at resisting vibrations. But the proportions, it's not guesswork.
So it's guesswork, yeah.
We do have informed guesswork.
I think it's called trial and error. Thank you. Great question. We have another question here. What's your name?
My name's Olivia, and I'm just wondering, can you separate an alloy?
Can you separate an alloy?
So you mean, Olivia, can you get the other things that have been added, mixed in, can you get them out again?
Oh, I don't know. I don't think you can.
Because when I was going to South Africa, and I met this bloke. This is the kind of thing you meet in an aeroplane. I met this guy as we flew into the airport in South Africa, and he said, he's just looking out the window, he said, they've got another aeroplane for me. And I said, what do you mean? And he said, well, they line up all the aeroplanes over there because I recycle aeroplanes. And they line them all up on the runway, and then he sort of literally takes them to pieces. And he said, we can't reuse the aluminium in the shell of the aeroplane because it's got stuff added to it. And you can't turn that into another aeroplane because no one will guarantee the composition of the alloy. And if you mix that up with other metals, you don't know that it's got a purity that you can rely on. And so it may have characteristics that you can't predict. I mean, something like an aeroplane is a bit too dangerous. So I think it's really tricky. But Dave, what do you think?
Basically, to separate something, you need to have properties which are different. So if you have an alloy with something with quite a low melting point, a very high melting point, or very high boiling point, you can kind of heat it up until the low boiling point one boils off, and you get slowly a more and more concentrated solution of one of them, and the other one kind of boils off. But if you've got two metals which are very, very similar, it gets very, very nasty. And I don't know if you've heard of the rare earth metals things like neodymium. They're actually not very rare. The problem is that when you find them, they're mixed all up together, and splitting them apart is incredibly difficult. And you can do it, but it's very, very difficult and messy chemistry.
Could you do it if you actually went down to the molecular level? Because I remember there was that video that was made recently where people were actually moving individual molecules around, and they made a little video of a guy playing with a ball. So if you went down to the molecular level, could you just hoik out the carbons?
So Caroline, how many atoms are there?
I guess in theory you could do that, but it would take a very long time.
Not maybe practical, but
no.
There's a question at the back.
Hi, I'm Jamie from Cambridge. I was wondering if you could explain how turbine blades operate at temperatures above their melting point. Is that correct?
Maybe we should just explain the context of the question. How do these turbine blades operate above their melting point? Because the reality is in these engines, the stream of gas going by is hotter than the metal melts at, isn't it?
Yes.
So you think, I've got an engine running here which has got stuff going on inside it hotter than the engine components actually melt at. Sounds a bit worrying, but the engines stay up there. How do they deal with that?
So it's a combination of two things. The first is we coat the blades in a ceramic, which has a much higher melting temperature, and it conducts heat through it very slowly, so it doesn't reach the metal. And the second reason, which sort of they work together, is that we blow cooling air through the blades themselves, which works with the coatings to stop that.
There's one more question here. What's your name?
Hi, my name's Freya. I have 2 questions. I was wondering how many parts would be in a common jet engine. And my second question is, how many metals would be in a common jet engine?
They're pretty simple there, Caroline. So how many bits to an engine? And
how many bits to a jet?
and how many metals? How many different metals?
Bits, a lot.
Is that an SI unit then?
Yes. So with the jet engine, you've got the discs and the blades and the shaft, which do the main amount of work. But then you've also got the casings, and they all have to have sensors on them, so there's lots of electronics all over them, so lots of parts. For different metals, well, in a jet engine you'll have steels, titanium, and nickel-based alloys. They're your main 3. But within those alloys, you'll have a lot of other elements. In some cases, up to 13 different elements that you've thrown in there.
13 in one alloy?
Mm-hmm.
And you know exactly what composition of all those different elements there is. It's amazing.
Yeah.
No wonder it's so expensive. Thank you very much, Caroline Goddard. You're listening to The Naked Scientists. This is a special edition of the show, live from the Cambridge Science Centre, where we've brought half the population of Cambridge, well, not quite, to come to see a show with me, Chris Smith, with Dave Ansell, with Ginny Smith, and our panel of guests, Margaret Stanley, Caroline Goddard, and Rod Jones. You see that the rate at which I can do that increases as the programme goes on. Time to get experimental now, with your help, because it's over to you guys who are here as our panel of the public this evening. Give yourselves a round of applause. We're going to get experimental. We need your help.
Okay, so if everyone looks under their chair, you should find a rubber band. So we're going to need your help for this one, and we're all going to have a go at this experiment together. And our panel, I think, has a rubber band, each of them. Good. So Dave, what do you need us to do with these rubber bands?
So these are perfectly normal rubber bands. Hopefully you've all found them. And what we're going to be doing is looking at the temperature of the rubber band. Now, about the most sensitive part of your body for measuring temperature is your lips. So what I want you to do is touch the rubber band to your lips and get an idea of what sort of temperature it's feeling like.
Now, we're mainly doing this to make you look silly, just to point that out.
Everyone with rubber band moustaches, it looks wonderful from up here, I can say so. And then what I want you to do, if you stretch your rubber band slowly, you'll find a point where it starts to get quite stiff. You can feel that? Okay, so what I want you to do is let it unstretch. Now feel the temperature on your lip, take it off, then quickly stretch it to the point at which it gets stiff, and then feel it again. And then leave it out and let it unstretch and feel it again, and see if you feel any difference.
So if we go over to our panel, are you guys having a go at this?
Hi.
So can you feel anything different?
Feels warmer when you stretch it.
Brilliant. Is that what everyone else is finding? Yeah?
There's some pretty weird-looking people here.
Yeah, I think
elastic band moustaches.
It's a good look. So all we've done is stretched a rubber band and it's got warmer. Why?
So that kind of makes sense. As you stretch it, you're putting a load of energy into it, and that energy must be going somewhere. And in the case of rubber band, it's going into warming up the rubber band. So the rubber band has got warmer as you stretch it. Rubber's actually quite a strange material. It doesn't behave like a normal material. If you stretch a piece of steel or any other alloy, you kind of stretch bonds in the molecules and you kind of store energy. But rubber is different. Rubber is made up of great big long molecules, a bit like this piece of rope. And when you stretch it, you're not stretching the bonds. What you're doing is you're straightening out the molecules. Now, did you notice what happened when you let it shrink again?
So everyone's saying it got colder when they released it and then felt it again.
That's right, because when rubber unstretches, what basically happens is you've pulled out your rubber molecule and made it nice and long and straight, and then you let heat, so all the molecules inside are bouncing around because they're hot, everything's jiggling. As it jiggles, it kind of jiggles around and gets more zigzaggy and gets wriggly, and so it gets shorter.
So what Dave's got here is he's got a piece of rope, which is pretending to be the molecules inside the elastic band. And when he wiggles them about, of course, the rope sort of makes waves, goes all snaky, and then the length of it gets shorter because it's moving around more. And that's what's happening inside the rubber band.
That's right. And as the molecules bash into it, they lose a little bit of energy and they get colder. So as the rubber band pulls against your fingers in order to shrink, the molecules lose some energy. They're actually losing it to your fingers as you pull in, and it gets colder, and you can actually feel that on your lips. You've effectively made a very, very small, very inefficient fridge.
So when you're hot, and probably not at the moment because it seems to be absolutely freezing outside, but if we ever have a summer again, you just need a few rubber bands and you can cool down no problem.
I'd like to see the machine.
Thanks, Dave and Ginny. So, any questions about elastic band physics? One just here. Look.
Or anything else.
Or anything else. Physics, chemistry, biology. Get your thinking caps on. We're into the last few minutes. What's your name?
Freya again.
Hello, Freya.
Doesn't the rubber band have the temperature of the room temperature, or is it its own temperature?
So if you leave a rubber band for a long time, it will get the room temperature. And actually, that's kind of why it works as a fridge. If you stretch it, it gets hotter. And if you leave it for a while, it'll get back to the room temperature because the heat will leave it because it's hotter than the rest of the world. And then as you unstretch it, it kind of itself gets colder. And so it cools down a bit. And then again, if you leave it for a long time, it'll warm up. So if you leave it for long enough, it will get to the room temperature.
One just here.
Hi, my name's Grace, and I've wondered what makes a magnet magnetic.
So magnets have little poles inside them. They have little elements that have to line up to make them magnetic. So if you've ever wanted to make a magnet, you can do it by using another magnet to rub along a piece of iron or something like that. And what that does is it lines up all these little poles inside them. And then if they're all pointing in the same direction, you get a magnet. And you have to be really careful with magnets because you can demagnetize them if you jumble all those poles up again. So if you drop a magnet hard enough, it'll jumble them all up and then it won't be a magnet anymore. And also if you heat it up. So like we were just talking about, when you heat things up, everything inside it gets really excited and jumbles around. So if you put a magnet in a flame, you can demagnetize it as well.
And the reason why, if you get to really fundamental things as to why anything is magnetic, magnetism is kind of effective electric currents. If you've got an electric current flowing, you get a magnet. So if you put a wire round and round and round, you get an electromagnet, and you put current through it, you get an electromagnet. Actually, in a magnet, on average, you have more electrons going around the atoms in one direction than the other direction. So actually, even permanent magnets are little electromagnets, and they, yes, become magnetic.
There's a question at the back here.
I'm Lily, and you said when you stretched the rubber band, you made an inefficient fridge thing. So how does a fridge really work?
Okay, so a fridge sort of does something similar by using gas. So if you squash your gas, I don't know if you've ever pumped up a bicycle tyre very, very quickly, the end of your bicycle pump gets quite warm. So if you squash your gas, the gas gets hotter. So what's happening at the back of your fridge is there's a pump which squashes the gas, then it gets hotter, it then has that long wiggly tube at the back which loses that heat. You then set the squashed gas, which is at room temperature, goes inside the fridge, and is let to expand. And if you expand the gas, it cools down again. So if you ever used an aerosol can for a long time, it starts getting really, really cold. So you let the gas expand inside the fridge, then it gets cooler, sucks energy and heat out of your food, then gets cycled back round to the pump and gets squashed, and then the heat is lost and it goes round and round and round, and the fridge gets colder and colder.
Fridge in 3 easy steps. Last question down at the front. Have you got a question for us? What's your name?
Jacob.
What would you like to know,
I
Jacob?
want to know what if you snap a rubber band, would it still do the same things?
Yes, so if you snap a rubber band, all that's happening is that those molecules there have pulled apart, but if you used a different area of it, it would still work. Probably wouldn't work so well if you used it right at the end because there's not much to stretch there. But yeah, it should still work.
And guess what? You can take the elastic band home with you and carry on experimenting in your own time. We've run out of time, so I'd like you to say a very big thank you to Dave Ansell and Ginny Smith, and to our wonderful panel of people, Rod Jones and Caroline Goddard, and also Margaret Stanley. Thank you very much to the Cambridge Science Centre for hosting us. Thank you, Guyton Lee, and also on the sound this week, Dominic Ford. Thank you also to Tom Simpkins at BBC Radio Cambridgeshire, who helped us to rig all the sound. But most of all, thank you to you for coming, because it couldn't have happened without you. I hope you've had a really good time. You can follow up more of these science experiments on our website, nakedscientist.com. In the meantime, though, happy experimenting, and we hope we'll see you at the next event. Good night.